Hello everyone, today we will be solving w19 QP21. First question. Chlorine can be prepared using the following reaction. MnO2 reacting with HCl to produce MnCl2 plus H2O plus chlorine. Here, Mn has oxidation state of +4. Cl has oxidation state of -1. Mn has oxidation state here of +2 and Cl here has oxidation state of 0. So from -1 to 0, chlorine has been oxidized, and from +4 to +2, manganese has been reduced. So MnO2 is reducing itself to oxidize chlorine. MnO2 oxidizes chlorine from -1 to 0. State what you would observe during this reaction. Since we are producing chlorine, which is a gas, so we will be observing effervescence. The halogen, chlorine, bromine and iodine are all volatile elements. State and explain the trended volatility down the group 17. Okay, so we have fluorine, chlorine, bromine, iodine. Now down the group, here we see that these are gases and these are solid. So we see volatility decreases. So first point is going to be volatility decreases. Volatility decreases down the group. Second point will be there is an increase in increase in number of electrons down the group, which increases induced dipole. So if you're not clear about what is induced dipole, a small explanation here. Two fluorine molecule bonding together will have minimum amount of electrons between them, thereby the electrons has a least amount of chance to actually shift. So partial positive, partial negative in the side where there is more number of electrons. But when it comes to iodine, the electron cloud is pretty big. So we'll have here partial negative, here partial positive, and thereby iodine will have more induced dipole between another iodine molecule compared to fluorine. Chlorine undergoes disproportionation during many chemical reactions. Write an equation for the reaction of chlorine with cold aqueous sodium hydroxide. Explain why it is a disproportionation reaction. Okay, so first of all, what we need to notice here is that it's a reaction between cold aqueous sodium hydroxide. Cl2 is going to react with NaOH to produce NaCl plus NaClO plus H2O. In cold state, chlorine reacts with sodium hydroxide, 2 molecules of sodium hydroxide, and chlorine goes from oxidation state of 0 to -1 and also to +1. So from 0 to -1, this is reduction. From 0 to +1, this is oxidation. So this is reduction, this is oxidation. Since oxidation and reduction is taking place at the same time, that's why this is a disproportionation reaction. So our answer will be chlorine is oxidized and reduced. Chlorine is oxidized and reduced. One of the product of the reaction of chlorine with hot aqueous sodium hydroxide differs from those in C1. Identify the compound that is formed in this reaction that is different from that is formed in reaction in C1. So now the noticeable thing here is that hot aqueous sodium hydroxide. So if you are using hot aqueous sodium hydroxide, chlorine is going to react with NaOH to produce NaCl plus NaClO3 plus H2O. So to balance this out, 3Cl2 will react with 6NaOH to produce 5NaCl and NaClO3 plus H2O. So as we can see, NaClO3 is a different product which did not form in the first reaction. So the answer will be NaClO3. Next, state and explain the use of chlorine in water purification. Chlorine kills bacteria and microorganisms. Chlorine does this by reacting with water and producing hypochlorous acid. So HCl, chlorine gas reacts with water to produce HCl aqueous plus HClO aqueous. HClO is hypochlorous acid. Hypochlorous acid is mainly responsible for killing bacteria. During your exam, only this highlighted portion will be required as an answer. Under certain conditions, chlorine undergoes a free radical substitution reaction with ethane. State the condition required to initiate this reaction. So this is a free radical substitution. Free radical substitution requires ultraviolet light. Write the overall equation for this free radical substitution reaction. So first of all, ethane is C2H6 reacting with chlorine to produce C2H5Cl and HCl. Well, this is just the overall equation. If they are asking for the mechanism, then you would have to show the entire mechanism. Question number 2. Complete the table to give details of the type of bonding and structure shown by some of the oxides of period 3 elements. Okay, first one, we can see sodium oxide, boiling point 1275. Usually whenever the boiling point is really high, it indicates that this is an ionic compound. Whenever it is a basic, then it obviously indicates an ionic compound. So type of bonding will be ionic. And structure will be giant lattice structure. That's because ionic substances are giant. Magnesium oxide, boiling point 3670, basic, ionic, and giant. Aluminium oxide, okay, again same indication except that it is amphoteric. So I'll again go for ionic and giant. SiO2. Well, now whenever the melting point is really high, that means this is a macromolecule and it is acidic, thereby it is a covalent compound. So covalent and giant molecular. SO3, boiling point pretty low, acidic, obviously covalent, and obviously it will be simple because boiling point is really low. Explain why the boiling point of SiO2 is much higher than that of the boiling point of SO3. The reason is very simple. SiO2 has many strong bonds. One silicon is bonded with 4 oxygen covalently, and then each oxygen is bonded with 2 silicon, and then it continues in this way, forming a very giant molecular structure. SiO2 has many strong bonds, whereas SO3 has weak intermolecular forces between molecules. So higher amount of energy, is required. So higher amount of energy is required to break the bonds then to overcome the forces between molecules. By the way, if you're wondering how SO3 molecules looks like, SO3 molecule looks like this, with a bond angle of approximately 120 in between them. They're covalent compounds and has very weak intermolecular forces between one molecule and another. Al2O3 is amphoteric. Explain what is meant by the term amphoteric. Use chemical equation to illustrate your answer. Okay. Amphoteric are substances that react with both acid and alkali. So amphoteric oxide reacts with both acid and alkali. So equations to prove our point. So first of all, aluminium oxide reacting with an acid, Al2O3 reacting with hydrochloric acid, HCl, will produce AlCl3 plus water. As you can see, there are two aluminiums, so to balance this out we'll need a 2 here, and that makes 6 chlorine, so 6 here and 3 H2O. The equation is balanced. Now the second equation that we're going to show is aluminium oxide reacting with NaOH. Whenever aluminium oxide reacts with NaOH, it also reacts with water along with it to produce NaAlOH4. Now to balance this equation, since we have two aluminiums in the beginning, we'll have 2. We'll require 2 sodium hydroxide and 3 water. Okay, so the water part being explained is 6 hydrogen over here, 2 hydrogen from here, and here we have 8 hydrogens multiplying by these 2. State what you would observe when a small sample of Na2O is placed in water. So the solid will dissolve obviously because Na2O will react with water to produce NaOH. To balance this equation up, we'll require a 2 over here. The equation is balanced. So obviously the solid disappears here, it turns into aqueous. And another thing to observe here is that the formation of NaOH will be exothermic. However, if you haven't done the reaction, you wouldn't know that. So the solid disappears. In this question, selenium is a group 16 element which shows similar chemical reactions to sulfur. Selenium reacts with fluorine to form SeF6 molecule. Predict the shape of a molecule of SeF6. So we know SF6 and we know it's octahedral. So selenium SeF6 should be octahedral as well. Most stable oxide of selenium is SeO2. Gaseous SeO2 reacts to form a solid polymer as shown in the reaction. One SeO double bond is replaced by 2 SeO single bond to form a polymer. Del H minus 346 kJ per mole. The bond enthalpy of Se double bond O is 514 kJ per mole. Use this data to calculate the bond enthalpy in kilojoule per mole of SeO. Our first focus is we're going to break one of the bond. Once we break one SeO, we are forming 2 SeO single bonds. So to complete the polymer, I'm going to draw few more bonds just so that we're clear. So as you can see, one SeO bond, and the second SeO bond is over here. Now to do the math, it's gonna be bond breaking minus bond forming equals to enthalpy change. So enthalpy change will be del H. Now bond breaking is 514 minus bond forming, since we don't know the value, so it's going to be 2 into Se single bond O equals to del H is minus 346. So 2 SeO equals to 346 minus 346 and minus 514, negative here. Finally, SeO bond equals to minus 346 minus 514 divided by minus 2 equals to, the value is going to be positive 430 kilojoule per mole. So the answer is plus 430 kilojoule per mole. SeO2 shows similar chemical reactions to SO2. Okay, so this is an equation to show the reaction of SeO2 with aqueous sodium hydroxide. Now, if we are doing a reaction of SO2 with NaOH, the reaction would be as follows: Na2, SO3, and along with that we would be forming water. So to balance this out, we would have to put a 2 over here. Alright, 2 sodium on the right, 2 sodium on the left, 1 sulfur, 3, 4 oxygen on the right, 4 oxygen on the left. This equation is balanced. So the same equation when repeated for SeO2, SeO2 plus 2 NaOH, the product would be Na2SeO3 plus water. Next question. Crude oil is a natural source of hydrocarbon that are used as fuels. Hydrocarbons with low relative molecular mass are used as fuels in industry, in the home, and for transport. There is a high demand for hydrocarbon with low MR. Name the process by which long chain hydrocarbons are broken down into shorter chain hydrocarbons. Easy. So the process should be cracking. Give one reason why hydrocarbons with low MR are suitable for using as a fuel. Okay, so I mean hydrocarbons with low MR burns easily. I mean, if you have used methane in your kitchen, you know it ignites pretty fast. Incomplete combustion of hydrocarbons can release carbon monoxide into the atmosphere. Write an equation for the formation of carbon monoxide from the incomplete combustion of butene, C4H8O2. Incomplete combustion would produce carbon monoxide along with water. Water will be produced. So 4 carbon monoxide and 4 H2O. So the number of oxygen is 8 on the right hand side, so 4O2. Identify an analytical technique that can be used to monitor the levels of CO, carbon monoxide, in the atmosphere. Outline how this analytical technique may be used to monitor the levels of carbon monoxide. Well, there is no way of detecting carbon monoxide by any chemical test or such. So the best way would be to detect the carbon oxygen triple bond, because this is a signature to carbon monoxide. So infrared spectroscopy can be used. And then compare the wavelength, because comparing actually allows us to detect. Compare the wavelength. C4H4S is an organic compound that is found as a contaminant in crude oil. Construct the equation for the complete combustion of thiophene. Include state symbol in your answer. C4H4S liquid burning in presence of oxygen. A complete combustion would produce carbon dioxide, it will produce water, and it will produce sulfur dioxide. So to balance this out, we'll need 4 carbon dioxide, 2 H2O, 1 SO2. So the number of oxygen on the right hand side is 8 plus 2 plus 2 equals to 12. So 6 O2. State symbols would be liquid, gas, 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 and gas. Okay, we can consider H2 as a liquid when it cools down in the standard room temperature and pressure. A student carries out an experiment to determine the enthalpy change of combustion of C4H4S liquid. Explain the meaning of the term enthalpy change of combustion. So whenever we say enthalpy change of combustion, we are actually meaning this term, del HC. Enthalpy change when 1 mole of a substance is burned completely in excess of oxygen. It is called enthalpy change of combustion. The student uses the following apparatus in the experiment: thermometer, copper container, water, fuel burner containing thiophene, calculate the heat energy released in joules by the reaction. Assume that 4.18 joules of heat energy changes the temperature of 1 cm cube of water by 1 degree Celsius. Assume no heat is lost to the surroundings. So first of all, our M is equals to 200. Our del T is 37.5 minus 18.5. Formula will be Q is equals to MC del T. 200 multiplied by 4.18 multiplied by 37.5, 18.5, okay, equals to 15884 joules. So the energy that will be released will be 15884 joules. If you notice, I haven't used negative here because they have already mentioned energy that is released. So I do not need to mention the negative. The student used 0.63 grams of C4H4S liquid in the experiment. Student used 0.63 gram of C4H4S in the experiment. Calculate the enthalpy change of combustion of thiophene. Include a sign in your answer. So to do this, we need to find out the number of moles that the student has reacted. So MR of C4H4S is 12 into 4 plus 1 into 4 plus 32.1 equals to 84.1. Number of mole thiophene equals to 0.63 gram, 84.1 gram per mole, gives 7.49 into 10 to the power of minus 3 moles. Now, since we want to find out the del H combustion, so we will have to divide this value by 1000 to turn it into kilojoules. 15884 divided by 1000 gives us kilojoules. Now, since this is an exothermic reaction, we will be releasing this energy, so we'll have to denote it by a negative and then divide it by the number of moles, which we have already calculated, 7.49 into 10 to the power of minus 3 minus 2120 kilojoule per mole. Next question, question number 4. CH3,3-CCHO is used in the synthesis of some antibiotics. Give the name of CH3,3-CCHO. So to name a compound like this, we must first consider who are in the straight chain. Since we can already see that 3 carbons are in the straight chain, 2 are in the side chain. So 3 carbon in a straight chain gives us propanal, and then we have methyl groups, so they're in the second carbon, so the name will be 2,2-dimethyl propanal. State the hybridization of the carbon atom labeled with an asterisk. Whenever it comes to hybridization, we need to first focus that the particular atom we are talking about, does it have a pi bonding or not? If it has 1 pi bonding, then we will just simply eliminate it from sp3 to sp2. So the asterisk carbon has sp2 bonding. 2 reaction sequences are shown. Reaction 1 is an oxidation reaction. Identify the reagents and conditions for reaction 1. Here we need to notice that we are turning an aldehyde into a carboxylic acid. When turning an aldehyde into a carboxylic acid, we need reflux and we need acidified potassium dichromate. So acidified potassium dichromate 6, and along with it we will require heat under reflux. Alright, so acidified potassium dichromate will act as our oxidizing agent. So next question, A. CH3,3-CCOOH is a solid at room temperature. B. CH3CO2-CH22CH3 is an isomer of A. B is a liquid at room temperature. Explain the difference in physical states of A, B with reference to any intermolecular forces that may exist. Okay, so the first one that we look here is we can see this carboxylic acid group. So this is a carboxylic acid. carboxylic acid. We should be very careful because trying to draw it out every time can be difficult. So hydrogen bond. A has hydrogen bond. So from the previous page we can also see here A has hydrogen bond. But then when they have mentioned about B, it easily gives away that it's an ester. It is an ester and thereby does not have a hydrogen bond. However, I'm gonna draw it for you just for the sake of understanding. CH2, CH2, CH3. As you can see here, there is no hydrogen bonding. There is no possible chances of hydrogen bonding. No hydrogen bonding. All right. So the answer will be A has hydrogen bonding. Hydrogen bonding. So A has hydrogen bonding, whereas B only has dipole forces between molecules. You can also call it van der Waals forces. A has higher boiling point since hydrogen bonding is stronger than van der Waals forces. Give the balance equation for the reaction of CH33CHO with NaBH4 to form S. Use H to represent an hydrogen provided by NaBH4. Okay. So S. All right. Now, as we can see that there is an aldehyde. CHO means an aldehyde. So whenever there is an aldehyde, if we reduce this, it's going to turn into an primary alcohol. So our main focus is going to be in that group. So CHO plus, we're going to put the hydrogens. We'll require exactly 2 hydrogens. So we'll put a 2, and then the product is going to be CH33 H2OH, a primary alcohol. I think some of you might actually want to have an explanation for this, or the mechanism, how does it work. So I'm gonna go ahead and do it for you guys. CH33 CH3 COH. As you can see, this is an aldehyde, and aldehyde will reduce themselves to primary alcohol. So it's going to be CH3 3 CH OH. This is the new hydrogen that has been added. Alright, so I've color coded it so that you can actually have a nice look at it. Draw the structure of the organic molecule T that reacts with A, CH33CCOOH in the reaction to form U, T. Okay, so when looking at T, here this is very clear that CH3 is here, CH3. So this molecule that we are talking about is propan-2-ol. See here, CH3, C, H, and obviously there was an alcohol on top of it. So the molecule T suggests a catalyst for the reaction 2 and structure of the organic molecule T. Since we have this in a skeletal formula in our previous page, we should answer with a skeletal formula. So propan-2-ol. Catalyst will be a few drops of sulfuric acid, concentrated. So concentrated sulfuric acid. C. So XYZ are all isomers of CH33CHO. A summary of some of the reactions and properties XYZ are shown in the table. Now, the properties that we are actually trying to look in here is the observation with failing solution. First of all, it says that there is no reaction. And then we see a principal absorption spectra, infrared spectrum of 1715 cm. Usually the 1715 cm is CO double bond. So if there is a CO double bond but it doesn't have a reaction with failing solution, and since there is only one oxygen, so therefore this must be a ketone, cannot be an aldehyde. So 2,4 observation with 2,4 DNPH should be an orange precipitate. Next, observations with failing solution, red precipitate, and 1730 cm. So again, this is a CO double bond. There is a red precipitate with failing solution, so thereby should be an aldehyde. And since this is an aldehyde, we'll have an orange precipitate with 2,4 DNPH. Observation with 2,4 DNPH, there is no reaction. So this is not a ketone, neither an aldehyde. There is no observation with failing solution as well, so there is no reaction. We can see a peak of this particular compound as 3000 at 3200 to 3600, 1630 and 1050. Now since we have a peak at 3200 to 3600, which will denote that this particular compound will belong here. So it can be a hydrogen bonded alcohol. Now until this far it's a guess. You will have to refer to your data booklet page number 14 for this particular question. CO double bond. As you can see, amide, ketones, and aldehyde and esters. I have used these informations to actually detect the first part of the question. Complete the table with expected observations for the reactions of X and Y with 2,4 DNPH. Well, this is done. This is done. Identify the functional group present in Y that causes the recorded observation with failing solution. Identify the functional group present in Y that causes the recorded observation with failing solution. So we have to write the name here, aldehyde. Okay. Y has a chiral center and exists as a pair of optical isomers. Okay, state what is meant by the term chiral center. Okay, so a chiral center is usually a carbon that has 4 groups attached to it. Okay. Draw the optical isomers of Y using the conventional 3-dimensional representation. So, to do this, let's first originally draw whatever we have in hand. CH33CCHO. If you notice here, this carbon has no chances of becoming asteroic or chiral. So to do that, what we can do is we can reduce the number of carbon from here, put a hydrogen, and make this into an ethyl group, and that turns the carbon into a chiral carbon. Now, since we are going to be using a conventional method, let's use it as our basis. Then central carbon dash, and then dotted. Opposite one is going to be dotted first, okay. So CHO, hydrogen, CH3, C2H5, C2H5, CH3, H, CHO. Z. C5H10O has branched carbon chain. It shows geometrical isomerism. Complete the table with bond responsible for each of the principal absorptions seen in the infrared spectrums of Z. So between 3200 to 3600. As we can see, between 3200 to 3600 we have hydrogen bonded alcohol. 1630 cm is equals to carbon-carbon double bond. Now you might be wondering that it also equals to CO double bond. However, it's not going to be CO double bond because we have only one carbon. 1050 refers to CO single bond. CO single bond comes between 1040 to 1300. Draw the skeletal formula of Z. Now, considering everything here, since we have a carbon-carbon double bond, and we have total of 5 carbons, so first of all we should consider the carbon-carbon double bond, and then it has geometrical isomerism as well, so must have different groups. So we can try to put a methyl to fulfill our number of carbons, another methyl to fulfill our number of carbons, along with a hydrogen, and now we have 4 carbons covered. We need one more carbon, and we also need the alcohol group. So could be like this, the structure. So counting the number of carbon, the structure is like this. Draw the skeletal formula of Z. So Z skeletal formula will be like this, with the double bond, and OH. You can do the other way around, it's still the same. X contains a carbonyl group. X reacts with HCN in the presence of a small amount of NaCN. Okay. To form C2H5 2COHCN. Draw the mechanism of the reaction of X with HCN. Okay. Alright, from this structure we are already getting the understanding that we have a C2H5 CO double bond C2H5. So first, the partially negative oxygen will take away all of its electron from the carbon-oxygen bonding, and a cyanide with its lone pair will then attack this particular partially positive carbon. In the second step, C2H5 CO minus C2H5 CN. In this next one, we will have a hydrogen cyanide. Now this molecule is partially negative on this side, partially positive on this side. So cyanide will take away all the electrons from the bonding, leaving the hydrogen vulnerable, which will then the oxygen will attack the hydrogen. And in the next step, we're going to have this along with a CN dot dot minus, which is basically this CN is going to be the starter for the next reaction. State the role of NaCN in this reaction in C7. Well, it is acting as a catalyst because it's going to provide the first cyanide. The reaction is with hydrogen cyanide, but the sodium cyanide is going to provide the first cyanide because sodium cyanide will be able to dissociate as shown in this reaction. Sodium cyanide will be producing Na plus Cn minus. Okay, thank you everyone for being with me until this far. We have solved in today's class Winter 19 question paper 21.